Now this one, like I said, this is the standard. This is the standard equation. Like this, the n over dt is the standard equation. You see that there is an minus b, and then they put it out in a bracket. This one is still equals to this one you get. So this dp dat is equals to this one, standard equation. They say where a is the birth rate of prey population, b is rate of prey due to the rate of loss of prey due to the interaction between the prey and predator. Rate of loss is just trying to say death. D is death rate of predator. C is the rate of gain of predator from prey. You get. Now they are non-dimensionalizing this equation. The reason for non-dimensionalizing most times is to balance the equation or to reduce the equation sometimes to the simplest form. You should have seen it in the GSTs that it is there. So we do du when normally they will say u of t, normally it's dn over dt, but they will change it later to u of t by non-dimensionalization. You get. So it's non-dimensionalization that changes, so u of t is equals to n of t, then v of tau and u of tau is equals to ut. These are parameters that they predefined so that they will try to make it simple. If you notice, you see that at the end of the day they'll be having simple formulas like u into 1 minus v, and the v over the tau is equals to alpha v into u minus 1. That is the and you see here f1 uv, f2 uv. That's as function 1 in terms of u and v, and function 2 in terms of u and v. That was the reason to non-dimensional. One of the reasons to make it to be reduced to the simplest form you get. Now for a steady state equation, this capital D is a formula on its own. D says that differentiating f1 with respect to du and differentiating f1 again with respect to dv. And the second one here, this third one now, is say differentiating f2 with respect to u and differentiating f2 with respect to v. Now this is a matrix form, meaning that if you differentiate those values, you put it in the respective places. You differentiate this one, put it here. You differentiate this one, put it here. Differentiate this one, put it here. You see that you have a matrix, a 2 by 2 matrix. You get. So let's say I differentiate f1 with respect to du. Now if I differentiate this f1 with respect to du, I'm having differentiating u, I have 1, then 1 minus v is a constant. See 1 minus v here. You get. I think they put this VO just to show that it is still in the initial state where nothing has been applied to it. Do the same thing and differentiate the same f1 again with respect to v. You see that if you differentiate with respect to v, u is a constant. So if you differentiate v here, you have 1. If you differentiate 1 here, you have 0. But since it is differentiating with minus, actually minus 1, which is minus u, you get. Do the same thing for here, do the same thing for here, you have your d. Now a steady state is where you have this formula. We state that d naught is the initial state. That's what it means. D naught minus lambda L. I lambda, I is the identity matrix. Identity matrix is 1 0 0 1. You get. So the d is like d minus the identity matrix times lambda. You get. Now lambda is just multiplying by lambda. If you multiply this by lambda, you have another matrix equal to here lambda, here 0, here lambda. You get. So now performing this d minus lambda, you get on this one. Now you having things like, let me do it, I'm just limited space. Since we already had our d, you know that it is now d minus I lambda, and we have already gotten our I lambda from the identity matrix and lambda multiplication. You get. So it is doing this d now, our d naught. You get. So it is 1 minus v minus the first term of that lambda, because see it is lambda 0 0 lambda subtracting of matrix, it should be by row, but it should be lambda here. You get. Next one now will be minus u minus the here in for that is 0, so it is 0, so minus u remain. Then here it is the next one, it is alpha v minus 0. See 0 here, which was the next time minus 0. Then the next term is alpha u that minus lambda, because lambda is the last one here. You get the gist now. So but at steady state we test it at different points, and we have to test at the points where it will give us, where the matrix will give us 0, where our d minus I lambda is equals to 0. We are testing points. That is why you are seeing this point 0 0 1 and 0 1 and 1 0. This is the point where u is 0 and v is 0. This one is the point where u is 1 and v is 1. This is the point where u is 0 and v is 0. You get, you test it, then perform the matrix operation, make sure it gives you 0, and if it gives you 0, that is a steady state. Bam, finish.